Hello, everybody. We're so happy that you are tuning in and are able to join us for this awesome episode of Alien, Astrobiology Lessons for an Interdisciplinary Exploration Network. So, my name is Ariel. I am an undergraduate student studying biomedical sciences and data science, and I'm super interested in astrobiology and in interdisciplinary collaboration. And I'm here with my co host.
Hi, my name is Charlie. I am also an undergraduate studying astrobiology. I am super interested in how life originated and ideas about laws that govern life overall as a whole. And we are here also with a guest today, Joshua Daymude from the Biodesign Center.
Yes! So Josh is from, as Charlie mentioned, Biodesign at Arizona State University. He's assistant professor in the School of Computing and Augmented Intelligence. And he's at the Biodesign Center for Biocomputing, Security, and Society. He researches algorithmic theory for the efficient coordination and characterization of collective emergent behavior in biological, social, and engineered complex systems. So thank you so much for being here, Josh. We're very excited to have you.
Yeah, I'm absolutely stoked to be here. Thanks for having me.
Awesome.
Okay, well, let's just jump right into it. So the first question we have for you is, as someone with a math and computer sciences degrees, has working in the Biodesign Center offered you any insights into how and why interdisciplinary collaboration can be useful, innovative, and generally awesome?
Yeah, absolutely. I like to joke with my computer science students when I'm lecturing and teaching that we're not a real science if you think that all of computer science is just programming. Programming is a software engineering, it's a discipline. Science is about asking crazy questions and then doing stuff to try and build evidence for answers to those questions. And all these folks who want to be good software engineers, no shade against them, but that's not science because we're not asking questions. Computers are a tool, and whether or not the tech pros would like to admit it, other sciences predate us by hundreds of years. There have been other techniques around for a long, long time. So I was very fortunate coming up out of math and computer science both, and then doing research as an undergrad and a PhD student, really getting to do stuff alongside other sorts of scientists the whole way. So quite a few physicists in the beginning, and then a handful of biologists later. So always had this eye towards how can computer science be sort of one instrument being played in the orchestra, but not necessarily the thing that has to run the show. But yeah, biodesign is a total dream in terms of getting to live that out now as faculty. We are one of, I think, currently 17 centers. Sorry, Josh LeBert, if I've gotten that wrong. I think we are currently 17 centers in the Biodesign Institute. We're really the most computational out of everyone, not to say other folks don't do computation, but we're the ones who sort of have a handle on the theory, the algorithms, the how, what's weird ways of approaching these problems. So getting to brush shoulders with people who are in the wet lab doing actual stuff, Esther Florsheim this week, with new publications about allergies and figuring all this stuff out. It's just so cool to be in the same building. Dream come true for someone who was purely math and CS for a long time.
That's really cool. Is there any way, I think this is sort of, me generating the question, not really thinking about this, but is there any way you could describe what biodesign really is to people who don't know about it?
Yeah, absolutely. I assume there are folks from beyond ASU as well who might come across this. So
Yeah.
I can talk a little bit about that. So at Arizona State, there are all your academic departments, right? So School of Life Sciences, School of Earth and Space Exploration, School of Computing, right? There's all these different schools. These are the degree granting pieces of the university. We have students, we have programs, academic programs where people are getting degrees. This is all under an umbrella at Arizona State called the academic enterprise. It's sort of what you would think of when you think of the university. Biodesign, the Institute, is part of a different arm of the university called the Knowledge Enterprise. This is not a degree granting part of the university. This is purely focused on research. So it's not that we don't interact with other parts. I am also in the School of Computing. I teach. I have students who are getting PhDs. Everyone here is doing something. But biodesign is organized differently, right? Instead of around a discipline, we're all biologists, we're all physicists, we're all chemists, we're all whatever. It's really organized around problems instead. So these 17 centers are focused on 17 slightly overlapping but mostly different problems. Like there's a center on neurodegenerative diseases. There's a center on health through microbiomes, right? So thinking about how the, sort of the brain-gut health axis works. There is a center right next door on biosensors, so building wearables and other kinds of engineering devices that are tapped into the sort of the biologically relevant data. So that takes all sorts, right? In a given center, you can have lots of different disciplines represented with people from all over the university, but united around particular problems with lab equipment and students and training dedicated towards solving those problems.
Wow.
So that's biodesign in a nutshell.
Awesome.
That's so cool. Yeah. Go ahead,
Definitely.
Charlie.
I think that's a good time to kind of segue into asking sort of what you do at Biodesign and ASU, and if you could kind of explain, this is a related question, collective emergent behavior in a bit of a nutshell.
Yeah. Let me tackle what I do first, and then I can kind of talk about our center and how I fit into that second, if that's okay. So my research generally falls under this term collective emergent behavior. So let's unpack that. There are things that one individual can do. There are things that one individual can do alongside others. And then there are really cool things that happen when many individuals interact together. These so-called emergent behaviors because they emerge from the interactions and do something that's more than the sum of its parts. It's beyond what any one of them is individually capable of. The textbook example of this is flocking by starlings. You've probably seen videos of this on YouTube, just these flocks of birds doing these beautiful dances that look like they're pulling apart and then coming back together. You don't see one bird anymore. You see, maybe to use a slightly controversial word, a superorganism, right? You're seeing this blob of bird that seems to be doing something beyond what any one bird is perceiving or intending to do, and yet each of them are playing a part in this broader thing. You can also think about emergent behavior, maybe outside of the organismal level. You can think of this in social processes. So the way in which people in communities and societies inform one another's opinions, right? And have influences over one another. How does that drive a whole collective of people to make a particular kind of decision or feel a particular kind of way about a topic? Is there someone leading that? Is that bubbling up from the bottom? Is it a mix? These are also kinds of collective behavior sorts of questions. So it isn't all like flocking and foraging and bio, those are often examples. And then maybe we could also think about this, right? My bio says engineered systems. We can think about this also in the things we build. So for example, as a computer scientist, thinking about the way that software is engineered. This is starting to get a little bit more into what the center does and less what I do. But you could think of it as the very mechanical process of someone who hopefully was trained to do this and isn't vibe coding. Spoiler for how I feel about AI, we'll get into that later.
Awesome.
Hopefully someone who is trained is sitting there smacking away at the keyboard writing code, and yes, that's like a skill and they're doing it. But is that really what's happening? No, I mean, they're looking things up online, they're reading the documentation, they're on Stack Overflow being like, how did someone solve this problem before me? They're asking their more senior colleague, like, have you run into this problem before? So at the heart of everything I'm talking about, it's that nothing is independent of interaction. Everything we're doing is interaction. So even the things humans do, like engineering, have these collective behavior sorts of questions to them, like, are we building things in a reasonable way? Is the way we're sharing knowledge done in an efficient way, in a way that is representing diverse opinions, representing the best expertise? The ways in which these things organize, and you sort of, again, it's no longer one programmer, it's a super organism, it's a blob of programmers, it's the whole industry, it's the whole everyone creating this software ecosystem that we depend on in all of the various ways that we do. How does that system zoomed out evolve, change, get updated, get maintained, when importantly, at the end of the day, it is these individuals, these birds, these ants, these birds, these cells, these people making these local decisions that really have no scope into this big thing that's happening. So connecting the local and the global, the small and the big, the interactions and the emergent. That's what this is. This doesn't tell you what I do. This just tells you what collective emergent behavior is, but hopefully that helps a little bit. At the risk of kind of talking too long, I come at this from maybe a slightly different perspective than the average complex systems person. Not that complex, I don't mean to be reductive. Complex systems people are awesome. They do cool things. I work with them. They're great. But let me give you an example. A typical complex systems person might set up a system of differential equations saying how things are changing over time, and what makes it complex is that they're nonlinear and there's a lot of them and they're interacting in weird ways, and you put it into whatever your favorite thing is and you integrate, you see what happens, right? Like, or you do real math about it or whatever. A lot of people think in this kind of dynamical systems way. I fell into complex systems very sideways. I was not trained as a complex systems person. I wasn't originally thinking about collective behavior. What I was thinking about for my PhD was something called distributed computing theory. You're probably comfortable with the idea that nowadays computers talk to each other. We have the internet. A lot of times, giant data centers are doing big, hard things all together with lots and lots of computers that your laptop is not doing by itself or whatever. So that's a whole way of thinking about how do you make that do interesting stuff? How do you do it efficiently? You now have to worry about computers talking to each other, managing communication, managing division of labor, managing all these things. So I was a theoretician, a pure mathematician who was thinking about distributed systems from a very task-oriented point of view. I have a set of entities, let's call them computers or agents or something. I want them to together do task X. So what are the instructions I need to give to each individual such that when we run them all together, X happens? It was a very design and engineering kind of approach to the problem. But as it turns out, design and engineering is just the reverse of, whoa, look, behavior X is happening and we have no idea why, but it's super cool. Can we guess at what the individual actions and interactions are that produce X? Sort of the reverse question. So sometimes we're starting from our capabilities and trying to make a behavior happen. Sometimes we're seeing a behavior happen spontaneously. We're trying to explain it at the individual level. So very broadly speaking, that is what I do using a variety of mathematical and theoretical computer science tools.
So this is so cool. There's so much there too. I mean, when you talk about dynamical systems, the thing I think of is that like general truism that boundary regions are always going to be the most interesting that you could possibly find,
Sure.
Which is just present everywhere. And I think it's pretty cool to apply that to a thought experiment when it comes to interdisciplinary collaboration, which basically everything Josh is talking about is interdisciplinary collaboration. And that's why biodesign at ASU is so cool. But when you have these boundary regions, say between disciplines, you get the most interesting things happening. You get people collaborating and coming up with new things and focusing on specific problems instead of, relegating themselves to factions based on their field. So I think that's one of the really cool things that I picked up on from that. And then I mean, collective emergent behavior is so cool. I know that I've had a little bit of experience looking at how ants become superorganisms, individuals within a colony. And then, of course, the example of cells in a person or just in any organism is super interesting. And Charlie, I know that, so Charlie and I took an astrobiology class last year together, and that's where we met. And there was one of our discussions, we sort of were thinking about collective emergent behavior because we're wondering about, constituents of a whole, and then the sum of all the parts, which is the whole, and whether something can be considered alive if it's a constituent of all this. If we think about a civilization as being alive, if we're trying to define life as astrobiologists like to do, what are all the parts of this civilization? Could they be the material things we're creating? Somebody could say that is, an individual piece in the whole that contributes to this giant superorganism of just a population of, humans on Earth that are making these crazy structures that you could see from space. So it's like, how do you define that? And Charlie, if you have anything to add.
No, I just completely second Ariel's question here, and wanted to add in that the general complex adaptive approach of just differential equations that you integrate over time sounds exactly like some research I'm working on right now, so you're definitely very correct in your description.
Wait, Charlie,
I want to be clear.
Oh, sorry.
Go ahead, Ariel.
I was just going to ask if Charlie wants to expand on that just a little bit, because that sounds pretty cool.
I can give a brief rundown. So I am working in Cole Mathis's group. If you're familiar, Josh, I think you actually helped with the code on the microbiome scaling project. And so basically, I am helping out with that and trying to figure out, on a large view, how we can program the coexistence of several microbial species in a set environment, in a simulation environment as well, with specifically accounting for the fact that these species' properties and physiology changes with the volume of the cells.
Oh, Charlie, we have to talk. I spent a year of my life on that project as someone who is not a differential equations person. So yeah, I have been working with Stephanie Forrest, with Cole Mathis, with Chris Kempes at the Santa Fe Institute.
Yes, so a familiar name to me.
I am somewhat grateful that this project is in more capable hands now. I will say I was a little out of my depth. But that's delightful. I'm excited to connect after this and hear what
Yes, absolutely.
That's great. Okay, well now I'm excited about microbiome ecology and programming mixes of things, and that is not what the question was.
That's okay.
The question was something else. Can someone remind me?
I think we're transitioning into this idea of how can emergent properties show us sides of the universe on any scale you might feel comfortable talking about that aren't generally seen.
Well, it should be Cole sitting here and not me, or Sarah Walker, or Lee Cronin, or someone who actually understands this. So I'll say this as an outsider for those who might be listening to this who understand assembly theory much better than me. Don't come yell at me if I got something wrong here. I'm doing this as an outsider, as a public service to educate. And I've just said the names of the people who you should go talk to if you're actually interested in this. But zooming out for a second, complex systems has been obsessed with different versions of the question you just asked. But really the core question is, how do we quantify or set thresholds for complexity? Like, what is complexity? Like, when do we say this thing is complex and this thing is not complex, right? And there's a whole history of different ways that, at least from kind of a mathematics point of view, people have talked about this. Cole actually has a whole class on quantitative measures of complexity that he teaches grad students. I'm going to blindly highly recommend that because I went through his whole reading list with him while he was prototyping this, and we had a blast. So it ranges all the way from philosophy, like Occam's razor, and well, maybe let's not talk about simplicity. Let's not talk about complexity. Let's see if we can get a handle on simplicity. What is that?
Yeah.
Do we know that when we see it? if that is the opposite of complexity, and maybe we could debate that. Maybe it is, maybe it's not. But do we even have a good philosophical grasp of what is simplicity? Does it mean it's like small in some sense of small? Is it easily describable? Like I can say a small number of words and have described the thing. Is it not that it has an aesthetic elegance to it? And it's hard to put a finger on what that means, but I know, especially as a mathematician, when I am looking at something mathematically elegant and beautiful, and in some sense it is the simplest and most beautiful representation of that idea. This is like a thing that math people are obsessed with.
And just to quickly interject, like when we are talking about Occam's razor, it's the simplest explanation is the best one. Is that me saying the correct?
Precisely, yes. So okay. I mean, what does that even mean?
Yes.
When? In what context? What is that exactly? So, but anyway, there's long history. I won't do the whole thing, but lots of different kind of math that has been used to try and say how complicated something is. And just as a computer scientist, I will offer the computer scientist version of algorithmic complexity. And then we'll skip all the other ones, which are arguably more interesting, but I gotta do my due diligence as a CF person here. So as a theory person, I mean, we love questions like this. We look at problems, so things you want to be able to do. The easy example is like, I give you a list of numbers, I need you to put them in the right order, right? This is the problem of sorting. Or I give you a large structure and I need you to find something inside of it. So what's the most efficient way of going through this large structure and finding the thing I want? For you all, that might be like a special feature of a molecule or something, I don't know. Like, think of the most complex data you can, and then you're trying to find something nice inside. There are all sorts of problems, and that's not what this podcast is about, so we won't, dig into that. But you can imagine that there are things we want to do, and then you can also imagine that there are, quote, good ways of doing it, and then, quote, bad ways of doing it. In the sorting example, a really bad way of doing it is going over the whole list, and then finding the smallest thing you saw, grabbing it, and putting it somewhere. Then going over the whole list again, finding the next smallest thing you can find, grabbing it, putting it down. Why is this bad? Well, because you looked at the list like so many times. This was so slow. What if instead, like every time you were scanning through and you saw two numbers out of order, you just like swap them, and you just swap things every time they're out of order? Well, it turns out you have to scan over the list way less times, right? So there's like good ways and bad ways of doing things. And when I say good and bad, I'm usually talking about fast and slow. That's usually what a computer scientist is talking about. So for us, the complexity of a problem is defined as the fastest way you can do something, like the speed of which you can do the thing. If that speed is fast, it's an easy problem. And if that speed is slow, it's a hard problem.
That's so
right?
Cool.
And what's really fun about this is that there's a lot of problems we have no idea, right? We have a problem, we have some way of doing it, but we don't know if that's the best way. So we can't say that's the complexity of the problem because no one's proved that that's actually the best way to do it. So it has this, we know how to do something, so we can at least go this fast. And then we have these things called lower bounds. We know you can't go any faster than this. No algorithm can go faster than this. And you're trying to kind of do all this math to make them meet in the middle. And once you have an algorithm that is at the speed limit, you know it can't go better than that. You have characterized the complexity of the problem, and we're done and we can move on to something else.
Wow.
This is kind of the whole field of theoretical computer science.
Wow. I do have a quick interjection. I think I doubt this would be the case, but do you ever run into a situation where there is only one way to do things?
Never.
How?
Never. As I say never, I'm like, ooh, that's an absolute word, and I need to think. I don't, unless it's like a trivial problem, like write me an algorithm that just spits out the input you just gave it or something. So like, there's nothing to do. I don't know. There's always so many ways of doing things. Many ways have the same complexity. Some are not, right? So So anyway, this is only one way to think about it, though. I mean, right, we're computer scientists. We have an unhealthy obsession with efficiency. Time is not the only way to think about what is complex or simple in this world. It is our contribution. I say our scientific contribution to this conversation is this way of thinking about complexity. Assembly theory, which I've had the recent pleasure of starting to mess with, is not a time thing at all. It's a structural thing.
Yeah.
I'm going to butcher this, but the core conceit of assembly theory is that molecules don't particularly happen randomly, and some structures under this randomness are just so much more unlikely than others. So if you see a lot of these so-called complex structures, it's unlikely that happened by accident, and this might be an indication of something like life detection. There must be some engine or machine or organism or whatever that produced this, because it doesn't happen under thermodynamics or whatever. So my lab, in parallel, I should say, to Sarah Walker and Lee Cronin, are working on algorithms for computing this thing called the assembly index. It's what assembly theory uses for how complicated a molecule or a structure is. So I jokingly and proudly say we have the second fastest implementation as we speak, because Sarah and Lee's project is definitely faster than ours right now. But anyway, we like to think about these algorithms in the formal way that we do that. We like to explain why it's fast and slow and all these things. So anyway, that's both kinds of complexity in one. We are building fast algorithms for computing complexity measures. So here we go.
Wow. How interdisciplinary of
Yes.
you.
How interdisciplinary. We're doing it.
In the assembly theory, I remember, one of the key concepts there is abundance. Like, it has to happen more than once. It can't be a universal fluke or something. Is there any way either of you could expand on this? Because I think you both know more about this than me.
That's going to have to be a Charlie thing. I do not do any evolution or selection pieces of assembly theory.
I also barely do.
I look at a molecule and I tell you how structurally complicated it is. That's all I do.
All I know is that it matters just about as much as you do, Ariel. And that has to happen. And that's called the copy number. So if anyone is more curious about that, that's the term to look up in assembly theory literature.
Should have Cole on this podcast.
Yeah. Okay.
You'll be hearing from us.
Super interesting. One of the things that I remember us talking about when we went over that in class is the difference between like a rat and a giant rock. You have this giant rock that has like a lot of complexity in it, but it's like the rat has this giant evolutionary lineage and tons of natural selection that went into that, and like that's part of it too. It's like a big comet tail on the thing you're looking at, and all of that is factored in. So that's a cool thing to consider. Is like if you just held up one thing here and one thing here, and you were like, which one is like a bioindicator? And I know like a rat and a rock sounds pretty simple, but like we can get like so like intensely ambiguous with this. But that's why assembly theory like is super important to astrobiology, and that is super cool that we got to talk about that.
Yeah, and we're extremely lucky. I mean, the theory is controversial for lots of reasons. I should say this. Probably the most critical arguments against it are that it is just repackaged other earlier versions of complexity, like Kolmogorov complexity, which is another thing that has fallen out of sort of computer science, sort of other things, probability theory. So I think we are incredibly privileged to have a bunch of the originators of the theory and people who think about it here at ASU, because it kind of means we get to see this pretty interesting and new thing happen in real time. It's not often that you get to do that in a scientific space, is like see a totally different take on how we should think about something happening before your eyes. So anyway, I'm very appreciative of the theory and getting to watch this happen.
One thing I wanted to add to my statement earlier, because I don't think I was very good about adding this, is that like the rock itself, while it has complexity, you don't like find another rock with the exact same versions of all of those molecules in the exact same positions with everything being exact. It's like this rock and this rock are not bioindicators, because we don't see that this isn't due to random chance, like that this complexity is not due to chance. So that's kind of what Josh was mentioning before. And if you're curious, definitely, I mean, there's so much to read about it. So, yeah.
Yeah, I mean, just to violently take a hold of the steering wheel of this conversation and shove it somewhere where I'm more comfortable.
Yes.
There is an enormous amount of cool stuff you can do, talking about randomness as if it's sort of the baseline, right? Thermodynamics as if it's sort of the uninteresting baseline. Going back to the engineering thing, there's an amazing number of algorithms and things that I have worked on for collective behavior that explicitly used the ideas of equilibrium statistical physics and thermodynamics to do things, like really non-trivial things, in ways that arguably were way more elegant and required way less resources than how you would do it if you were carefully writing your rules and your algorithms and making the little robots do things. Physics and randomness and thermo and whatever can be tools, can be engines to produce behavior. That's not how a bioindicator person would think about that. That's just the thing in the universe. That's background noise. We're looking for something that's different than this. But just, there's cool things you can do with it.
That's a good point. If I was to just interject something basically off topic, which is yes, let's do it. But there's so chaotic motion is not random motion, but chaotic motion can basically generate outcomes for us that you might not expect. So kind of similar to what Josh is talking about. For example, a lava lamp has chaotic motion going on, so everything's kind of going in directions that you don't know. It's unpredictable, but you do know every step that all these little particles in the lava lamp took before that one and before that one. And because of the unpredictability, you can literally create seeds for random number generators to protect, to do crypto protection. I don't think I'm saying that word correctly, but it's pretty cool. So,
That's so cool. Yeah. You started talking about that, and I was like, oh, that's cool. I wonder if you can use that kind of randomness as you can extrapolate that to other things. I would not have looked at the lava lamp and thought cybersecurity, but
that's what I was looking for. Crypto protection. Yeah.
Yeah, I am trying to be helpful in keeping the conversation on the rails, so I'm not going to jump into crypto and all the cool things. But yes, the idea of, I want to be clear, this would be called pseudo-randomness. Okay. It appears random. It is entirely deterministic once the initial conditions have been set. This is also like chaotic motion in these things. I want to be clear, what I was talking about before is actual randomness. You would actually, unless you are a full-blown all the way down to the quantum level, philosophically a determinist, which, fine, okay, we can have that conversation. I am talking about actual randomness, not something that just appears random, but really is. You can harness this as a tool for behavior.
And that is an important thing.
You can harness things that look random but are not, also for other things. All kinds of things.
Yes, an important distinction, because chaotic motion is deterministic but unpredictable, not random. You have these initial conditions and everything. So yeah, there's a lot to go into there, but I appreciate the distinction, because that is.
And then one thing I just wanted to add in real quick is deterministic refers to something where you know what the end result is going to be from an initial set of ones.
It does the same things in the same order every time somehow.
Yes. So just to clear that up, make sure that that's known.
Yes.
Alrighty.
Okay. Well, since we're talking about life and looking at it and detecting it, another question we have for you is, would you consider AI or even just complex systems to be alive or to have any aspects of life or aliveness?
I am going to reject the premise of the phrasing of this question.
All right. We're here for it.
putting AI or even just complex systems in the same sentence is kind of wild to me. And I'm going to put it back on you a little bit to explain to me why you phrased it that way.
Yeah.
I would not have traditionally, okay, and I'm also going to put it on you to tell me what you mean when you say AI. I don't mean in a technical way. I just mean in a like, when you were dreaming up this question and wanted me to talk about it, what was the technology, the thing that you were thinking about when you were writing this question? Just so that we can be on board with what we're talking about. And then, yes, I will give you a long, fun answer to this.
Yeah, no, that's great. I'll tackle both. First, I'll tackle the AI part. I think what I was thinking of is the type of AI that is generally accepted to be AI when you're not talking technically at the moment, just because it is kind of, there's like an advent of a new type of machine learning that's being made available to the...
So we're talking about generative AI and large language models.
Large language models, yes.
Great. Okay. That it gives me the scope to answer this question.
Yes, but sorry. I was gonna say that there's also like just robots in general. So when I say, I mean like, you know, computers, and then, you know, going from there, to me, there's a lot of aliveness there that I can talk about to no end at a later time. But that's kind of where the AI question stems from, is just because AI is topical at the moment. But in general, I think that, you know, robots being created by organisms that we think we know to be alive, us, and being literally like our, you know, in a way, I could term them like our offspring. You know, we're creating them, and they have an evolutionary lineage that has us in it, that has alive creatures in it. So that's kind of cool as well. But then when I was talking about the AI or even just complex systems, I think the reason I use the word even just is because I was going from something that's a bit more topical and approachable to a general audience, and then kind of like narrowing it down to something that you do study. So that's why I said that.
Okay.
But
interesting. Yeah. All right. I have a smattering of thoughts.
Okay.
I think the reason I object to the question is because it's sort of obvious that some complex systems are very much alive. We were talking about biological and social complex systems earlier in the conversation. I don't think anyone would really have fighting words about that being alive if we're talking about a flock of birds or a human society.
Right.
This is not particularly controversial.
How about the...
Now, if you were talking about something, say something physical, glass beads, a granular matter system, when pressure is applied to a whole bunch, like think marbles.
Okay.
If you push a whole bunch of tiny, tiny marbles together, they self-organize into essentially load-bearing structures where some of them are bearing basically all the pressure in these beautiful sort of networks of what are called stress chains, and a bunch of other ones are not. They're just sort of hanging out in the space. I don't think that's particularly alive, but it's certainly self-organizing in an interesting way. So, you know, this is a broader philosophical conversation about what do you mean by life?
Yeah.
What is that? Are we using the 4-rule definition, the 7-rule definition? Are we talking about something else? Is this a you know it when you see it kind of thing? Like, I don't know. This is not my area of expertise, so I'm not going to wade into something I'm ignorant about completely. But I think complex systems, I feel fairly confident just in like those examples I gave you, and I could probably come up with others. Complex systems can be both alive and not alive, and life, at least in my basic experience, is not like a direct function of complexity. Even the assembly theory folks, I don't think would say there is a threshold complexity. Once you've crossed it, it becomes alive. I think they would say this is an artifact of life.
Okay.
This does not happen with higher than random chance, like in high abundance, unless there is possibly something like life that is catalyzing this high abundance or whatever. So I think I want to be a little bit careful when we're talking about complexity and things. especially when we're talking about bioindicators, which again, it's not my world, but
Yeah.
we can, I know enough to talk about it. We're really talking about artifacts of life or indicators of life. We're not saying the thing has become alive
Okay.
itself. Maybe there are folks who think a lot about this. I'm not one of these folks. So, you know,
No, that's awesome.
I'm sure there are good theoretical treatments of this. This is not my world. So do I think AI is alive? No, like very firmly no.
Okay.
And I don't particularly feel the need to get super deep into what we mean by alive to say that, though it does make my answer maybe less rich if I'm not defining life and then saying very confidently, no,
it's okay.
It's life. It's absolutely an artifact of life.
Mm-hmm.
It is absolutely like the robots you're talking about, which I assume you mean these kind of humanoid or anthropic sorts of things that are meant to look like things that are alive. There's a bit of biomimicry going on. I absolutely feel that these are artifacts of life. We would not have built them if it weren't for us and if we didn't have some idea about why we wanted to do this. So no complaints there. A little bit, we'd have to have a longer conversation than I think the time we have left to figure out precisely why I'm drawing, where I'm taking one side of this line of I don't probably think these robots or these AI systems are alive. What these generative AI systems are incredibly good at doing is mimicking very believable looking textual patterns.
Mm-hmm.
So I would like to talk a little bit about that, but any questions before we dive into Gen AI and and
I think that I wanted to kind of like thank you for the complex systems part. I think what I was getting at is like whether you think complex systems are alive in general no matter what, or whether you think they're not alive in general no matter what. And it seems like it depends situation, which I think is really cool. And I think there's so many opinions on all three of these sides that we just defined, and yeah. I think that's really. I also really like the example of the load-bearing marbles, which is really cool. I wasn't thinking about that.
But I mean, clearly, at some point, way down, you've got subatomic particles, and then atoms, and then molecules, which most people probably feel comfortable saying those structures in and of themselves are not alive. And then you keep zooming out, and eventually you hit things that, from a sort of an anthropology point of view, are definitely alive. And clearly it changed somewhere at one of those scales. So yeah. Where did that happen? I don't know.
The eternal
so I'm
question.
Not saying Amp did this in a compelling way. I know all the things that make this muddy and hard. I'm just telling you, I'm not the expert.
Oh, yeah.
You on this call handling that question.
No worries at all. I like that we're getting your perspective as
sure.
somebody who works with these things, and then just seeing
totally.
like what you might think on it, because there's so much that informs you. And like, to be quite honest, like if you're not in a field that's directly focusing on this, there's a lot that's not noise in your mind when you are thinking about the topic. So I think it's really interesting. But yeah, Charlie, if you don't have any questions, we can go on to Josh's next.
Yeah, I'd say let's keep rolling.
Yeah.
Cool. I'm going to state my biases up front about generative AI. I am in both my personal life and in my academic life, I am probably the most skeptical and critical voice that I know about the sort of adoption and proliferation of these technologies. And anytime you say something like this, you have to do the caveats of like, yes, in a well-scoped problem with good data that's well documented and a good application of the methods, these absolutely can do cool things. And for that, I will point you to my colleague in the center, Hee-Wook Lee, who does some amazing things with LLM-like technologies for generating immune sequences, basically building new recognizers for unknown epitopes. And that's a lot of jargon, but basically it's like, if we've got a disease we've never seen before and we need to build drugs or whatever that bind to those things, but this is hard to do because it's this nasty three-dimensional physical structure. Like, how do you do that? Hee-Wook is doing some absolutely phenomenal work figuring out how to use LLMs to predict text that will bind to the text of these epitope things. But for him, texts are amino acid sequences and immunosequences, and he's doing all this cool stuff. That is a well-scoped problem. His results are great. It's working. So I want to be clear. When I say I am like highly critical, highly skeptical, I don't mean this in an absolutist sense. I mean this in this is not the everything machine. This is absolutely not the solve all the problems in this one way super intelligence machine. That's not what's going on here. What is going on, though, is something that looks like an everything machine. And this is the problem. It is exceptionally good at saying believable sounding strings of words on whatever until you look slightly closer and, the illusion falls apart a little bit. So I'm going to state my biases up front. I really, for lack of a better word, don't like these things. And it is
very respectable.
The burden of proof lies on the person using this technology to convince me that it is this technology that is going to do a cool thing and not any of the other stuff that we already had, especially given the insane resource usage and everything else around these things. We have been studying efficient algorithms in these spaces for a long time. These things are not efficient. So convince me, like Hibuk, that there's a good reason to do this, that I'm on board. But a lot of things are not. So pointers for people who are interested. The starter text I would do is Emily M. Bender and Alex Hanna's The AI Con. I think this is a very well-written, accessible primer on broadly how these technologies work and sort of the critical questions one ought to be asking around this space. If you're looking for something that's a little more like nuts and bolts, like how did all this stuff come together, Karen Howe's The Empire of AI is a little bit more of like a business human focus on like how did we get where we are, like slightly less technical, more like there were humans in the mix doing this, like how did we get here, what happened. So that's another very interesting thing in this space. So I live a little bit more in that world, I'll just say that. I think what's helpful for people, and probably someone seeking out the Alien podcast maybe knows these things, but at risk of duplicating what someone already knows, just to be incredibly clear about how these technologies work. You are giving them a string of, in the biz we call them tokens, but you can think of them as words or sentences or whatever. It's some unit of text. You're giving them a string and you're asking, what is the most likely next token, next word, next sentence that would come after all the tokens I've shown you so far? That's a completely reasonable question to ask. Okay, so where does this fall apart? Well, the training data. Where did the training data, how do we know what's likely and what's not likely? We just took the whole internet. We just took the whole darned internet and looked at all the words, and it doesn't matter what the internet was actually talking about, or if that information was real or not, or if it was wildly racist or any of the other things that we wouldn't want. We just took all of that text and we essentially, in a fancy mathy math kind of way, counted the number of times we saw these words come after those words. Awesome. Yeah. And then you just string words together that are, a high percent of the time, the words that you would expect to come next. And you know what the problem is we are evolutionarily hardwired in our sort of linguistic capabilities to associate the ability to manipulate language with attribution of intelligence. Because we have never had a reason in the entire history of the species to have an example of like, oh, this thing is speaking in a language I understand, but is not a human being. Like, nothing else is capable of this.
Right.
We are evolutionarily unprepared for this psychological thing that is happening in this moment. That's something that is definitively not human, but was trained in a probabilistic sense to mimic the patterns and styles and sort of stylistic signatures of human speech looks very believable. And that's not anybody's fault that you look at that and say, that seems pretty alive. That seems pretty human, because yeah, that's how we do language. That is like how we are wired to interact. But I'll land this piece with one example that comes out of the AI Con and is documented in many other places. In the 1970s, sort of after what was called the first AI summer, so Marvin Minsky and friends, kind of the founders of this space, who got a lot of money to do the first AI research in the late 1960s. Rosenbaum at MIT invented a chatbot in the 70s, to be clear. I mean, there's no big data, there's no anything, it's the 70s. He invented a chatbot called Eliza. Eliza is a classic sort of cultural touch point for a lot of people when they think about AI. Same thing like the AI from HAL 2000, like right. It's things people point to. Eliza was very interesting. It was meant to mimic a chatbot, but it had no machine learning-y things. It wasn't statistical. It was just programmed to understand the parts of speech in someone's statement, manipulate those parts of speech, and turn them into a question. So it would go something like this. I have a very hard time with this family member. And Eliza would say, okay, I, family member, da 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 da. Why do you have a hard time with that family? I mean, again, back to deterministic, right? This was like a rule, like take these parts of speech, put them in this order, frame it as a question, and spit it back out. Mm-hmm. There's nothing alive about this. It's just move the symbols around in the right order.
Right.
The number of people who hailed Rosenbaum as like, this is AI therapy. We've done it. No one needs to do therapy anymore. We have Eliza. And he was like, the whole point I did this project was to show like, this isn't intelligent. This is just, symbol manipulation.
Yeah.
But this is a perfect example of what I'm talking about. We're hardwired to interpret language and imagine a mind behind the language, the mind that had intent and ideas that it is using language as a medium of expression to communicate, that I would strongly posit simply does not exist in generative AI systems. There is not a mind, there is just a lot of data and a lot of nicely compressed probabilities, and it is good at stringing believable things together. This is not a particularly popular opinion, especially in computer science, but I think it's important when we think about the way in which we're using these systems and it's proliferating, at least across our contexts, to really understand what these things are doing and whether you want the synthetic text prediction machine to be doing what you imagine it to be doing. This misalignment is important to understand.
I love this perspective because, like when we think about the, I'm not saying that this is what I thought about when I thought about interviewing you, Josh, but like if you think about what the computer scientist's perspective on AI is going to be, it's like generally with bias, you may think that it's not going to include these thoughtful, considerations of the ethics behind AI and what's actually going on and how people are perceiving it. And so, like, I'm really glad that you've brought that up. And I'm not saying that, like, no computer scientists are going to bring that up. I'm just saying that the computer science perspective, because
to be clear, I am absolutely not the first computer scientist to bring this up. I am echoing other people's ideas in a space where I hope it's helpful. These are not original ideas. Yeah.
Totally. Yeah, and I just think that, like, for me, being somebody who might go in being like, oh, if I'm talking to a computer scientist that is not Josh, they might have not Josh's view. That's a bias that I have that I should probably eliminate. So it's all, but we appreciate that you've brought that up and everything. And I think that actually kind of goes pretty well into the next question, which is about your thoughts on, if STEM students should be exposing themselves to the humanities and taking classes in humanities and learning about culture and philosophy and tons of the things that you just drew upon to make your conclusions very eloquently. So if you have any thoughts on this, we'd be glad to hear them.
Yeah, I don't know if I'll comment on the students specifically. Students are a product of their life experiences combined with the education we presented, it's really not their fault if they're drawn to one thing or the other.
For sure.
Most students are just trying to like do the things we told them they need to do to get the degree and go on to the next thing. So I'm not going to bag on students specifically.
Yeah.
But yeah, more broadly, this question of like, is there sufficient cross-training between STEM and the humanities? Where do these perspectives come from? Are we preparing students well? I think this is a huge issue. Anyone who thinks that all of STEM, science, technology, engineering, mathematics, is somehow separate from the human beings who do those things is deeply confused. Science is not some abstract, otherworldly reality that like is imposed upon humans, like slowly being discovered. I mean, the world might be that, but science is a deeply human endeavor. It's like a whole bunch of people all over the world with questions in this like really bizarre training and apprenticeship system of how we actually do science and how it gets funded and how we decide what ideas to pursue and what not, what we like, all this is human.
Like it's an active process. Yeah.
To figure it out, to do the work, to like be highly caffeinated and grind that out and like figure it out. This is so human. Like to think that these things are separate, that these are not fundamentally human endeavors is a mistake. Now, the degree to which you need to be versed in the humanities to be a good scientist maybe depends on what you're doing. I lean towards it's nice to have some training, but I don't have any formal training in the humanities. I wish maybe now that I did. I like to read, that's helping. But in the day-to-day, when I'm like doing whatever I have to do, I don't necessarily know in the guts of getting my results how much humanities is happening. But when I'm thinking about connecting with other people, when I'm thinking about writing and presenting my results, when I'm thinking about the broader conversation that my little community of scientists is having and where that conversation has come from and where we're going, having some appreciation for the culture of that space, for the way other people have thought about this problem in other disciplines, like, I think this is useful. But I don't have like, here's my 10 books that every scientist should go read in the humanities, you'll be a better person, blah, blah, blah.
Yeah.
If someone else has that for me, please send it my way. But yeah, so I mean, I think it's important. I think the pragmatic reality is this is not particularly how we train people. We undergrads have these general studies requirements, right? You're supposed to touch a variety of things, but that's not done in a particularly intentional way where we're like trying to craft a particular approach to being a scientist, being an engineer, being a mathematician. So there's a lot of room for interpretation, but yes, highly underrated, very valuable. I, at least in my lab, do spend a lot of time with my students thinking about sort of the ethics and philosophy and social world that we are positioned in. That's important to me. Definitely.
And it seems like from what you were talking about, it's important to recognize that doing science is a lot more than like clacking away at your computer. It's an involved process, and to best prepare for that is to best immerse yourself in a variety of skills and disciplines.
Yeah. So many computer scientists and mathematics undergrads go into research thinking they'll do more computer science and math, and it's like, the greatest joke is that research is primarily about writing and talking to people about what you've done. And you're like, oh man, I got into this to not write. Like, this is not what I enjoy. And all of a sudden you're reading and writing for the rest of your life. But it's a beautiful thing. I mean, it opens you up. It's the classic things of like why you should read books. New perspectives, like people have had good thoughts about things before you existed. You should go look. It also holds for us. There's no reason why we should be exceptions to this.
Totally.
So, absolutely.
Thank you so much for your thoughts on that. It's been so wonderful to talk to you. Thank you, Josh.
It's been a great conversation. I'm so glad you were able to make it and interact with our club.
Yeah, really excited to follow up, see where things go. It's awesome.
Yeah.
Thanks for having me.
Absolutely. Alrighty, well, we hope you have a wonderful day, Josh, and anybody who's listening, and thank you so much if you're listening for tuning in and giving us your support in the form of just general attendance to what we're talking about. We will be posting another episode fairly soon, so keep an eye out for any updates. And here in the Spotify, you can find our link to our Instagram page and our YouTube channel. And yeah, we just really appreciate you tuning in. So thank you, Josh. Hope everybody has a great day.
Okay. Yes, thank you.